Hi, in this lecture 18, I'll first finish the discussion on MD simulations of this melt rupture phenomena. And then I'll move on to one of the most important chapters in the book on elastic yielding that involves step shear. So I will begin by reviewing in detail some of the key literature results. And then I will introduce what is known as damping function, indicate how I can construct a new function, which is called Q function actually, by looking at the behavior of the damping function. And this function shows non-monotonicity, and this non-monotonicity will allow me to discuss the so-called non-quiescent relaxation. And I will end this with some movies on this phenomenon.
All right. So last time I was hoping to give you some sense of how to understand the regime 4. If you recall the movie, basically you stretch something very fast. When you stretch fast enough, you'll find that the sample will really break up as if it was cross-linked. You saw it. It was breaking very, very sharp. And the sample fully recovers because it was all down in the limit that the sample did not yield. If you monitor the stress, engineering stress, you will find in this region 4, the stress just keep building up and then ruptures. So we were rather mystified by this, and this is certainly not something easily a tube model can prescribe. So apparently, this rupture is related to the chains undergo scission. At least some of the chains must have undergone scission. And as soon as it undergoes scission, it will, unzip. The chains will start to lose its ability to hold up to the network. So we were very intrigued by why this is possible in absence of crosslinks. And we had some idea more recently and realized that perhaps molecular simulation is a way to look at this problem. So we get hold, we have Professor Sigi, we had a joint student. So we got hold of a system and start to examine in this case by looking at a chain, how much chain tension it builds. Okay, chain tension that builds in there, in the chain. So for example, we could find many different chains, many different examples. For example, this chain 124 is one that makes 2 hairpins, and we can look at the chain tension that's building up there. So that is this blue line. This is the chain tension it builds along the chain. And if you read the level of stress, it turns out this is reaching a level of 0.1 nanonewton. That's a huge, huge number. Remember, it takes only 3 nanonewton to break the chain. So this is, let me see, this is, it's more than that, in fact. This is close to 0.5 nanonewton, actually. So it's quite large, very, very large amount of stress. And I will not go into any details, but to share some of the findings that we learned from the simulation. So for example, the nice thing about simulation is indeed it replaces what is impossible experimentally, which is to observe any given chain. So for example, this particular chain 124 is basically made of 2 hairpins. On one side, it's grabbed by one of the chain here, and on the other side, it was grabbed by a different chain on this side. And in the middle, it has some twist, as shown here. It's rather complicated. And the chain is so elongated in this limit because we stretched to a lambda of 18. So I would just be very brief about the complexity of it. You can appreciate many chains mingle with each other in some very complex ways, as you can see here. Indeed, almost like they form some knots. We later decide not to use the word knots, which is a very specific term, right? Knots means you really have to make a loop and tie it. But we start to call them twists. At least they twist in some complicated way that prevent them from sliding. So it turns out this simulation reminds us of this game of tug war. Okay? If you don't like the cartoon, here's a picture from the internet of a real tug war with elephant. We are very familiar with tug war, but in this simulation, it shows up in a very, very explicit way. And I invented a new tug war game called Tug Wars with Trees. So you can imagine have, instead of tree, of a metal post, okay? So you can actually have so let's say each of this arrow represent 10 men. So I can have 40 men on this side. And then with the rope wrapped around a post, then I can continue this tug war. And with 2 posts, I can have a complicated tug war like what I showed here. Okay? The post is slippery, so it turns out the force just keeps transmitting. Japan. Okay, it just keeps transmitting. So it's just a modified tug war. That would be one way. Of course, if you don't like that complicated way, you can just have a tug war like this with people on this side and people on this side. And you can almost tell me for sure, where is the maximum tension in the rope? In the very middle. It just accumulates. It does nothing else. It just accumulates. Okay? So for example, this will be, I call it 10 men each. This will be 60 men on each side, another 60 men on the other side. So you get a tension that's due to 120 men, or 120 human beings, men and women, are pulling. And the lesson you already learned is, you just said the maximum tension is here. What about the tension here? It's much less. Well, sorry. Right? It's much less. What about here? Well, it's still not high, but twice as much now. A little more, and eventually maximum. So that would be what tug war is. It just accumulates. What is interesting is, let's say if it's a tug war with no winners, nobody wins. That means both sides are balanced, right? That means even if I have a post, nothing, the rope was stationary, will not move around the rope. Everything is balanced. The lesson you learn is that you can have, remember, see, this is 10 people, 20 people, 30 people, 40 people. By this time, the tension here is huge. There are 40 people on this side pulling. It's huge. Yes, the tension here is huge, but it does not require the tension here to be huge, right? By definition. I think this is the lesson we learned, that you can manage to have a balanced state without the chain ends escaping from this Titan network. It just needs to accumulate. Well, this is really the explanation of what we found. What we found was something rather remarkable. This black curve is black line is what I showed you. It's the tension in the chain. What Ye Xin did was, for example, let's he get hold of this red chain. He will add the force of this tug of war people. He will add them up. All the forces add them up. The reason they add them up is the force is accumulating along the chain because of the connectivity of the chain. So he add up, he just find that force builds up, like the red lines. Just like tug of war, starting from small and builds up out there. And then all of a sudden, at this point, his protocol just keep adding the force. You find at one point, this force plunges down. If this is 13, he plunges down to minus 13. So this is what I use a cartoon to explain, and this is the plunging, that force. So basically, it confirms what we know, that there is this much chain tension, this much chain tension. It's all balanced by the fact there is this orange chain. That's acting the same amount, holding it. And of course, you can ask what the orange chain is doing. Well, orange chain is doing something the other chain is doing similarly to the test chain or black chain. And that's what apparently is the case. I just want to draw a cartoon where Yexing is still struggling to find the real chain showing this, because this 124 is this red chain. But he has plenty of examples where the tug war doesn't involve two posts. The tug war is just like this blue one. That they are just other monomers grabbing onto this blue chain on both sides and cause this to build a lot of chain tension. Cause it to build a lot of chain tension. And it just acts like one of the effective strands in the network. The rest of this history, meaning we are still in the middle of writing this up to publish it. But it tells you a very clear picture of how this entanglement network could manage to build enough chain tension in this network so that eventually the tension here is large enough for chains to break. And so it gave us some insight about this region 4, where we see the Mel rupture. Okay? Mel rupture. And this is, of course, is also the clearest indication that the network act like they have point-like interactions. Okay, so it's inconceivable to describe this feature using a smooth tube, because that does not capture the fact the interactions between chains are very heterogeneous, very, very point-like, very localized. Not something smoothly grabbing everywhere. And they make turns, right? They have tension this way, and then another chain has to be there to balance it. I thought I just want to update it because we were not able to do that when the book was written. Okay? So this was just a little update. So let me move on. In fact, let me take advantage of the fact we have this outline made for the recording. Let's move to part 3. I make this as part 3 because this topic stands alone. It is the most remarkable result in nonlinear polymer rheology involving entangled polymers. The most remarkable, the most unique in terms of conceptualizing what we see. For example, this term is uniquely new. Uniquely new. The phenomenology from which this term arises is also uniquely unknown before, until we start to look at this. So this really stands as a distinct part of nonlinear response. So far, you see, in part 2, we have been dealing with startup deformation. It doesn't matter, it's shear or extension. Basically, all of a sudden, you start to deform. So that's what we have been doing in part 2. And we recognize that process, if you are doing it fast enough, will reach a point of yield. In other words, the elastic deformation cannot proceed forever. Here, in some sense, is a much simpler case. But we didn't do the simpler case first. I will give you the joke. Why? Meaning, in research, we should always do the simplest thing first. Because simplest thing, you gain experience. And then from that experience, you can cope with more complicated things. That's how it should be done. And I will tease you about why we didn't do it that way. Okay? Why do I say it's simplest? Well, as you can I guess even this doesn't really say what I really mean. It really means upon stepwise deformation. In other words, at least I spent some time complaining to you that the startup continuous deformation in both shear and extension. Startup shear and startup extension. We just went through the idea that startup extension does not produce flow state, right? Steady flow. Its sample breaks apart. And in the shear case, you might have shear bending. And that's already a complicated thing in the sense you may start to ask, does shear bending survive in steady state? That's the most challenging question. Why I say that? I say that because to examine steady state, it would mean you have to shear it forever, right? Meaning forever, meaning shear it until your response is no longer time dependent. So it means you may have to shear many units. You may have to shear, let's say, 1,000 units. Well, that's a lot, meaning 1,000 edge. Keep shearing. And then you may indeed, your experiment may be terminated well before that because of edge fracture. So it's really demanding for you to learn about startup shear and learn about whether shear bending survives in steady state, because you may run the risk of sample suffering from edge instability. The sample just doesn't behave well when you shear for too long. Therefore, the simpler experiment, of course, is not to shear forever, but just to make a stepwise shear. For example, you may just shear by moving your upper plate 3H to the right and hold it. That's a much simpler story. You can avoid this edge effect. So we'll patiently go through that with you, with the example of shear, and then, as you may imagine, the same physics applies. Then we will look at extension. And then in chapter 14, we'll speak about a little more deeper about what network, what entanglement is really about, what it amounts to. Okay? So let me proceed with a description of this. Okay? So this is now part 3. We're going to be on chapter 12. And I will try to be rather patiently tell you what's going on, step strand, step shear, if you like. And I will, of course, introduce eventually the concept of so-called elastic yielding. But to begin with, I better do it with enough motivations for you so that you understand what a detour we took, meaning how we have taken several steps to reach that point instead of immediately doing something like this. Since it's simpler, it should be done first, right, as I said. But it was not done first. So let me remind you what is stepwise shear. Well, you can do it any way you want. But basically, if you prefer to think about, when you conceptualize it, you don't need to think about it's a cone plate or whatever. It's just simple linear shear. So you have H, and you move your upper plate X, and then of course the amount of deformation you produce is X over H. Well, that's not of course. Remember, the big assumption is that you manage to make this deformation homogeneously. Right? This is a big assumption. Without particle tracking velocimetry, you don't know for sure. You don't know for sure that this is the case. But for convenience, for discussion, let's assume we have achieved that. Okay? And of course, if you like to think about strand, it just means you start from 0, and all of a sudden you strand to a certain level, and you stop. And the step strand that we typically talk about, it just means that the time it takes to make this much deformation is very, very small compared to relaxation time. And that would be enough for you to claim that you have a so-called step shear. It's never instant. When I first learned rheology, textbook of course say it takes 0 time, it's instant. And we even later have reviewers always question sometimes about, gee, why you're not, why you're keeping TI finite? Well, I said, the machine cannot do it instantly. And as long as I know it's much shorter than tau, I know I'm in the theoretical limit of not allowing any any chain relaxation to take place. Okay. This is, of course, is also a wonderful place to speak about linear response one more time. Linear response in the case of step shear. What do we mean? Well, we of course mean that structure remains intact, unperturbed. What do we mean by unperturbed or intact? It means the entanglement remains entangled. The entanglement state is unperturbed. How do you achieve that? Well, you achieve that by guessing that the amplitude of step strand is small. Okay? So if you don't know your answer, of course you will say, oh, let lambda be, let gamma be, let's say 1%. That's definitely, it sounds small. But of course, this all depends. For your entangled melt, 1%, even 10% is fine. But if you have a highly filled polymer, then 1% may already be nonlinear because you have fillers that are jammed up so tightly that 1% would already start to destroy the structure formed by the filler. So it's a relative term, this limit of what is the linear response is relative for our untangled melt. I will tell you this is about 0.6. This we'll discuss in detail in chapter 14. 60% is about the limit where you can still have linear response. Well, right away it invites you to think what is nonlinear response. Of course, it means you're going beyond that limit, doubling it, tripling it, beyond that. What do we see phenomenologically? Well, linear response is strictly means the following. If you, I told you what to do, right? If you move your x, the top plate, you will stop at x0. And Ti over Ti amount of time. And then what you do, you of course, you in principle monitor the stress as a function of T. And since you are doing it in a way that you can capture, you can even watch how the stress grow up to T0. And then after that, if it's an untangled melt, there's no cross-linking, then you may expect, let's say, I know it's always convenient to have T equals 0 on it, but very often our data is desirably represented on double log plot, where I cannot plot 0 anymore, as you know. So your relaxation after that point may look somewhat like this. I know I didn't draw it smoothly, but something like this. It relaxes. Okay? To capture this relaxation, if this is linear response, then this relaxation is captured by some function called relaxation modulus. So it exactly captures this feature of how it comes down. Okay. If I want to save my space a little bit, I divide this stress. Then I will be able to claim that all my experiments fall onto the same line as long as my amplitude is smaller than linear response. All I'm trying to say is to indicate in that limit, the stress you produce is proportional to the strength you used. So that this quantity is independent of the amplitude you used, right? So as a result, I can use different strengths. I'll get exactly the same curve. Yeah? Right? That's the definition of linear response. Okay? If you double the amount of strength you use, you will double the amount of stress you produce, and therefore its ratio will not change. Everywhere along the curve, it will not change. That will be the linear response definition. Question? Huh? Yeah. You see, that I already deceived you. I only verbally said, I made an effort to plot this as double log. So being log scale, it stretches the initial times. So as if your stress is not decaying very fast. So it's very, whoever invented, discovered log scale, of course, we need to find out who did it. It's remarkable, right? It stretches short time so that you can put short time, long time on the same figure. That's the whole point. Yes, so if you draw it on linear scale, this thing may crash down like crazy. So don't be confused by that. Yeah. You follow? Don't? Yeah. So log scale is a very magic a tool for us to have. It stretches the short times and it compresses the long times. Okay, let's move on. This is a linear response. It's worthwhile to talk about it because only then you know what nonlinear response means. So nonlinear response, of course, means the amplitude is high, such that you no longer have a linear response. But operationally, it is not a crime for you to acknowledge that the stress is a function of how much you applied. Except whatever in front of gamma, as you know, should have the same unit as stress because gamma is dimensionless. So this relaxation modulus remain to be called relaxation modulus. You may not call it equilibrium relaxation modulus anymore, but it's a relaxation modulus. And now, nonlinear means that it acquires dependence on the amplitude. I know in my book, I actually omitted the zeros. Okay, which is, be my guest. For notational simplicity, let's get used to the idea that the gamma just means the amplitude of strand you applied. Okay, it's a constant because each step strand involves a certain amount of gamma. Okay. Let's review the whole history a little bit. And this is where we eventually discovered something that was not obvious. Okay. It just so happened that we can introduce this quantity called relaxation modulus, which really is a way to normalize your data, right? People indeed actually plot this, usually. They usually, let me emphasize, they usually do not plot sigma. Instead, they plot this normalized quantity called relaxation modulus. If you do so, plot as a function of time because you're watching the relaxation now. You tend to ask the following question. Give me the baseline. Remember we did strand hardening. There is a zero rate envelope. Here, the baseline is the linear response. Is this curve. That's the baseline. So you ask first, gee, please plot relaxation modulus, so-called equilibrium relaxation modulus. What's this? Right? So it turns out all untangled polymers, you get this universal curve that you may build a theory for. But let's see you have such a experiment done, linear response. So this is the limit where the data was collected in the limit of gamma being small. right? And now I'm going to make things complicated. I'm going to now I will do the same experiment, but I will change my gamma now. I will do an experiment with gamma like here. I will do an experiment where my gamma may look like that. And I know why did I do this? I meant to have different symbols. So and in fact, I can be a little bit more careful to indicate to you what happens. Which is this. So this is typically you see the data. There are some important features. I know this one I probably give me an opportunity to do it a little differently. Maybe. How about that? I know you have not seen anything I want to show. What I want to say is experimentally, it appears oops, sorry. That after a certain time, the stress relaxes in the same way. Remember, this is something, again, I want to emphasize, very, very powerful about log scales. Only in the log scales, in other words, your log is log of G and log of T. Forget about log of T. The log of G, the y-axis, for you to claim that they have the same trend, only log scale works. In log scale, a percentage of drop is the vertical distance. So if I claim this red, blue, and green behave identically, I mean the following. What I mean is over this time, if red dropped this much, over this time, my blue also drop that much, okay? Because they are vertically the same. In other words, if I do a horizontal shift, all the three curves will collapse. Because this thing may not be a straight line, so don't use the word slope. They have an equal separation, or the best yet. That's why I say log scale is powerful. For the same time from T1 to T2, the percentage of the drop is the same. In other words, your GT2 over your GT1 is the same, independent of the gamma you used. This is in the direction of changing gamma. Okay? And on log scale, it means the same vertical separation or vertical drop from that point to that point, from that point to that point. Same. I want to be really slow here because it's so crucial. So experimentally, we discovered long ago, since 70s, that at least after some point called TK, for some historical convenience or historical reason, after this point, these three curves are the same apart from a vertical shift. You can see the way I carefully draw. Of course, before TK, they are not collapsing. They cannot. In fact, right, my green circles is reaching the red instead of having a separation of some amount. Yeah. So this is a phenomenology that as I patiently use different strands, I find the later time stress relaxation are identical. And therefore, this is powerful information. We don't know the physics, or people start to try to figure out what is the physics. And this is a part that will eventually become the most fascinating part of a coincidence between experiment and theory. So basically, we know this is the fact. If this is the fact, which apparently is the case, I will, of course, explain to you why this happened this way from the new physics we know, as well as why this happens according to the tube model, the old theory. We will make everything out of the sense here, make sense out of everything here. But I want to be very patient here, proceeding. Because this feature is true, right, that for t larger than some magic number, tk, all G curves collapse upon rescaling, or basically a horizontal or vertical shift. So how do we do this rescaling properly? Let me use the available space here to introduce this quantity, very widely used in the literature. People introduced a quantity called damping function. Don't ask me why it's called damping function. It reminds me I should try to figure out why they call it. The whole idea of damping function is to recognize the universality here. This represents some universality. Something is universal. Fascinating. The universality is all relaxation after TK are the same upon rescaling for different gammas. Yeah. I will introduce it. Yeah, basically, literally means we can do a vertical shift, all the curve will collapse. But let me do it properly. Let's introduce this damping function called H, which really is just a way to capture how much I need to do the vertical shift. And it is defined as G, T larger than TK of gamma divided by G of the equilibrium. So it's quite trivial. It's based, remember, let me even do better, just to help you with the color. H. So I know we didn't use black, so this one is fine. So basically, I'm going to introduce H, which is nothing but this vertical shift that I have to do for each of the curve, right? Because I know, let's say I look at the green line, that's this one, okay? Green line is different from the red line just by this ratio, which is that vertical separation. It defines a pure number. for the green. So that would be my green. And I can do now next time for my blue line. I get another shift, right? And I'm going to then plot this H as a function of gamma. Fair? You can understand that this, by definition, the way I present it is going to be smaller than 1. Because that's what data shows me. Right? Meaning every curve is below my red curve. Okay? Yeah. This is very, very important. There are tons of paper continue to be written using the so-called damping function. So let me give you two things. When you present this data of stress relaxation, if you like linear, basically you are talking about really stress relaxation data. The way you do the stress relaxation experiment is you don't present sigma, the stress. Instead, you present everything in terms of normalized sigma. You present G. I emphasize this because it will come to really impress you what's going on. So let's move on and tell you what is H. So according to the data, H is going to start from 1 because that's when the gamma. That's when gamma is 0. That's the same as the red. So that's start from 1, and it's going to look like this. In fact, I wonder if I prefer to do it that way. Yes, I do. The only drawback about log scale is you cannot represent 0. But you can still represent 0.10. Okay, that's 1% deformation. That's tiny. Anything, in fact, anything below linear response. Log scale, now everything is double log now, okay? Double log scale now. Everything before that should give me unity, right? Okay. This red curve summarizes all the data. When I say summarize all the data, I really mean for a given polymer system, this summarizes all the stress response to the different value of gamma you applied to do the step shear. For a different system, you could be getting a different result, like this maybe. But let's talk about the important part of it. It turns out if you are really experienced, you will know from this data whether something fishy is going on, something really wrong is going on with the data. Remember, the data you collected, close your eyes, meaning you don't know what happened. Either during the step strand or after, you don't know what happened because we don't have PTV. We don't have movies. We have nothing. We just try to collect the mechanical information. By assuming, remember the essence of rheology is by assuming the strand field is already prescribed homogeneously. Not only during which, but also subsequent to the shear. That nothing should happen. If I make a step strand, let's say moved my plate to here, then not only I achieved so, homogeneously, but also after shear, I pretend everything should be intact, nothing should happen. I pretend because nobody teaches me otherwise. Nobody tells me after shear session, I know I'm jumpy a little bit, but why not? After shear session, we call it. Everything should be motionless. For sure. We are so confident that this must be true. Okay? It should be motionless. And therefore, if you come to me and say, oh, I want to do particle tracking velocimetry to see what goes on, what's going on, I would say, don't waste your time. Nothing happens. There's no need to watch it. Okay? Except when you examine the red line or the green line that summarizes the existing experimental data. You take a look, you discover something remarkable. Very remarkable. Double log scale. You find this slope. Oh, I don't have a good name for it. Did I use any name for it, for the slope? Let me do it differently so you know what I mean. I'm exaggerating. This is a slope of -1. Be confident about what we mean by slope on double log scales. P is the slope, right? That's what slope means. Yeah? So if P is -1, it just means Y is 1 over X. Yeah? Yeah? And you know how 1 over X behaves. 1 over X is something like this, right? Okay, if P, as I draw here, I may as well just call it P. If P is smaller than -1, which is what it is, right? It just means this is -1. It just means it's stronger. Right? So this much is known. In other words, you look at the data from 70s, you right away know this is the fact. That the slope of your data is smaller, is the H function, the damping function, is dropping faster than 1 over gamma at higher gammas. So this is the amusing part. I told my student that I'm now going back to do experiment myself now after 15 years. 15 years ago, I also had the urge to go back to the lab. After seeing P is smaller than -1, I all of a sudden realized something very big is to be discovered. And now let's recall what I complained. I said, people not only, in fact, let me emphasize this. Remember I called this damping function, right? In fact, if I advance my point a little more, people not only does not present data in terms of stress, rarely, I use double negative now, rarely do they present data in terms of G. Instead, they present in terms of H. How convenient, because we just want to capture the universal aspect of the stress relaxation, right? Things are universal when time is beyond some magic time. But upon seeing p being smaller than -1, it scared me. It tells you something very useful. First of all, let's recall what is h. You just try to recover it. Just try to recover what it's teaching you. H is g at some higher times. You don't even need to bother about that. And the bottom is just a function so that when you take this rescaling, it's no longer a function of time. That's all it has. Other than that, who cares? If you, what you care is about the gamma dependence, then who cares? The gamma dependence. Okay? So here comes. Here comes. I will play the magic we always do. In fact, this time is not so magic anymore. I'm going to examine not h, but h multiply gamma on both sides. Okay? What if I do that? What if I plot, what if I examine h multiply gamma? Why do I want to do that? I just indicate to you that just means g. What is on the top? Gamma times g is what? I'm going to examine on both sides. Yeah, I'm going to examine on both sides. On this side, I know what it is. Chaitanya just helped me. It's stress. So from the data in the literature, they didn't tell me what is stress, but I can recover it from their figure. Yeah, I can recover it. So this is going to be nothing but stress at long times. Yeah? As a function of gamma, crucially. On the left, I just revealed p is much smaller, is smaller than -1. Yeah? It tells me this quantity, as I approach to higher gammas, is a decreasing function of gamma. Because h goes as 1. H goes as gamma p, and therefore gamma p is I know I want to help you. That but for you guys it's okay. You don't need my help. This exponent is less than 1, less than 0, because p is higher than -1. Yeah, so this I proved. I just proved for you that this behaves as a decreasing function of gamma. Yeah, on the left. Yeah, according to the data. On the left. The right, it says this is nothing but stress at various times. What does that mean? Meaning, how do you reconstruct this? Meaning of this. This apparently is a decreasing function of gamma. Yeah? What does that mean? Let's say my TK is 10 seconds. Okay? I'm just trying to make it concrete for you. Let's say your TK is 10 seconds, empirically. Okay, it's 10 seconds. Okay? I'm asking ourselves, what about the state of stress? The state of stress, the level of stress. At t equals 50 seconds for different gammas. What does this say? Well, let me be real slow for you. Remember, I just showed you the data of the red curve, which is h function. Now, I'm going to examine that by multiplying gamma to that h. What do I see? What you can guess to be? Because after some point, it will start to decrease. And think about the meaning of h times gamma. The meaning of h times gamma is stress time for different gammas. What do you mean by passing the dashed vertical line? Translate now. What does this point mean, for example, relative to this point? Because after all, it just involves gamma 1 and gamma 2, right? Yeah? What does this mean? Come on. What does this mean? Gamma times h, which is the stress at longer times, is lower for the test that applied higher strain. Yeah? Let me repeat my English. Right, right. Nothing need to be yeah. Basically, gamma times h is the stress as a function of different gammas at different times, right? So, for example, 50 seconds satisfy this condition, right? For example, I'm looking at my stress at the 50th second, involving two different experiments, applying gamma 2 versus gamma 1. What does this plot show? It tells me at gamma 2, at 50 seconds, my stress will be lower. Yeah? By definition. I applied higher strain. When I wait, I find my stress is lower than the test I applied lower strain. How nonlinear can you get? I'm almost joking. It's no longer nonlinear. It is troubling. It is not possible. It's not possible, Dong. How can I apply more strain when I wait in both experiments, I wait at the 50th second? My stress that involved higher strain actually was lower. Right? That's the reality. That's the experimental data. Oh, I'm causing you to lose your mind because all this thing will be so obvious if your data was presented directly in terms of stress. Instead, you plot it in terms of damping function. So, let's look at one of the curves that I cannot draw better. Here are some of them. Here's certainly one of the dramatic ones. So dramatic that you will find it, there was something else as well. There's something else as well. But let's just entertain ourselves with this. Here is a piece of data presented in terms of G, the relaxation modulus. Okay? I can recover stress by multiplying gamma. These different curves are just different gammas. Yeah? So I can know the gamma, and I multiply each of the curve with the corresponding gammas. Okay? And recover the stress, and this is the stress. Over all the time scales, because I have the whole curve. Meaning, I now can abandon this damping function. I can just simply go back to E divided by, multiply G with gamma. I recover the stress for all of it. And this is the curve. You can see, oh gosh, in this case, very remarkably, the more stretched, the more sheared one is the black, the less sheared one is the red. Oh my Lord, this one is disastrous. Even at the beginning, the stress you produced with less strand was actually higher. I will explain later why it happens. How can that be? Do you have an answer? How can you have your stress being lower when you apply the higher strand? As soon as you stop shearing, you find your stress you produce was actually lower. Should I give you a short answer? What if you have a tremendous amount of wall slip, such that you think you applied this much strand, but because of wall slip, actually you generate very little strand to the system? Well, you have the book to read, so you don't need me to get into details. But this is the, if you like, this is the another patient reproduction of the experimental data. So this is, you can see, this is the same data as the first figure. Just for the sake of argument, look at the first figure. This is the first figure. Beautifully reproduced. It was presented as a function of G. As I promised you, the pink being linear response is stay at the top, and these are different gammas, 1.1, 1.9, 3.4, 10, 15 of the G. You multiply that G with gamma, of course you get this curve. And you can see, indeed, over a certain period, all of them more or less collapse in the same manner, universality. But the disturbing part is that this exactly shows there is a hump, that the stress if you look at the 100-second, for example, that is produced with gamma of 15 have the same stress as the stress produced with a gamma of 0.115 almost. And everything in between. In other words, for example, you can look at you can look at anyone you wish. For example, obviously you can look at the square, that's 10 is here, but 15 is lower. Right? 15 is the red one. And similarly, if you don't like that, you can have your 6.7 is the green one, is here, and 15 is here. So, so basically, and this is the curve that shows its slope is more than -1. So the end of the story is what I have already plotted for you, that there are certain. Let's see. I'm sure I have some somewhere. Oh, it is there. I just didn't. Here's the summary of the data. The experimental data that we just examined, if you plot it in this H function, it is this either red or the square. Basically reading that relaxation at different times. Basically, you can see they are non-monotonic, right? Beyond certain stress, the stress you produce actually is lower, right? Non-monotonic. So that's the careful analysis of the data we had. Okay, how can this be? You strain a small amount, you wait. And you strain a larger amount, you wait. You wait for the same amount of time. You find the stress involving a large amount of strain after you wait for a certain time actually was lower. This is crazy. How could that be? What could possibly have happened? You know, I can remember linearity versus nonlinear response. I can accept the fact you deviate from linearity. Deviate from linearity, it means the following. It means when I apply higher, let's say when I double my strand, if it's linear, then my stress should double. If it's non-linear, it should still be higher. When I double the strand, it should still give me higher strand. That's already non-linear. It doesn't have to be double. It could be just, change by 50% increase. But instead of that, it reversed. They become lower. So that's why I said this is not just a matter of nonlinearity. This is a disaster. So venture to guess what happens? And why I was motivated to go to the lab. So I went to the lab and tried to build a primitive version of the particle tracking velocimetry using one of the rheometers when the other students are busy with their other investigations. Because this curve really motivated me to think about this. This curve, the green, is the theory, actually. The green is the theory. We'll talk about next time because I think we are running out of time today. That's the other remarkable thing. The reason that damping function was so popular was not only because it is something calculatable according to the tube model, but it actually has a particular form according to the tube model. The disturbing part, you see, this having a maximum is the same as me saying that this P is stronger than -1. Stronger than, meaning more negative than -1. So that when I multiply a gamma, I couldn't cancel the effect. Come on, right? It's so elementary, right? Right? So that this exponent can still be negative. Right? That's the whole point, right? So, so I better end up this without giving you more suspense. We can talk a little more about the theoretical implications next time. I better not give you too much more suspense by telling you why we go to the lab. I went to the lab 15 years ago, eager to find out what this non-monotonicity means, what it means for stress to be lower. Didn't you just apply higher strength? Higher strength shouldn't be always giving you higher stress. Of course, our universe should tell us higher strength should always result in higher stress, even if it's nonlinear. But how can you have a lower stress when I apply higher stress? Okay, that's bizarre. That's bizarre because you are assuming something that it may not be true. So what do we have assumed? Well, this is the magic. We have assumed there's something nonlinear. Something's nonlinear. Fine. But higher strength should give you higher stress if everything follows. But there is one case you may not have higher stress after you use a higher strength. And that is the case. That is the case if, oh Lord. Oh gosh, let's not. Yeah, it is that case. I probably shouldn't do it in the play mode. Oh, Lord, we are so dependent on technology. And this PC is particularly slow. So in any case, I did it very slowly today. So here we go. This is the most remarkable findings of all. Let me give you a few points for it. Since you know your relaxation time, let's say your relaxation time is 100 seconds. Then as long as I move my H to the right by a factor of 3, within a second, I have been doing it very fast, right? Because it takes 100 seconds to do anything. But within that 1 second, I can use my movie to probe, to see if my 3H was producing something funny or it was still okay. And it's still okay. But now after scission, this turns out is exactly 3.2H to the right. What do you see? I'm sure you have seen it. I mean, you have seen. What do you see? It moves. It's not motionless. It moves and it's not motionless. I actually so this was what motivated me to go to the lab. This particular one eventually was produced by, probably by Xiang. because we eventually used a different rheometer to do it. I want to do my best try to confuse you here. I told you my motivation. Our motivation was to realize this part is a disaster. It's unphysical. How can you have this is being run? Okay? But even this part that didn't pass the maximum, okay, could already have the physics that produced this part. Do you follow me? For example, this particular movie, for example, oh Lord, I need to go here probably, yeah. For example, this particular movie may have produced something just on this side, may not have been on the negative side. In other words, let me drive home this point. The speculation I had from the beginning was to see the fact that the stress is lower at a higher strand is because samples break apart during the stress relaxation. In other words, if it breaks apart, you will, before TK, you could recover a great deal of stress by snapping back if there's something breaking apart. So that after TK, you don't have enough stress. But this one, the breaking may not be severe enough to have produced that. Nevertheless, it's not motionless. So this is the biggest surprise there is prior to this movie. Forget about shear banding. Remember I said we never invented the concept of shear banding. It existed before. It existed in many other fields. It existed in the symptoms of the tube model. But stress relaxation should always involve motionless samples. We should never have had this. I close it here now for today.